Okay, welcome to Unit 5 Recording 2. In this recording we will be summarizing the last recording about the different types of chemical bonds, plus we will be adding a discussion of metallic bonding, and then we'll get into nomenclature or naming different types of chemical compounds. So first let's talk about ionic bonding. And what we learned in the previous unit, electrons are transferred. Ions are held together by the electrostatic force of oppositely charged particles forming a crystalline lattice. Bonds are stronger than covalent bonds and have higher melting and boiling points. And these are electrolytes, which means when they are dissolved in water, they conduct electricity. Covalent bonds, on the other hand, the electrons are shared between the atoms, and these electrons can be shared either equally, which would be a nonpolar covalent bond, or they might be shared unequally, which would create a polar covalent bond. Electrons are attracted to the positive nucleus of all atoms, and you can think of these as having an electromagnetic force involved in the bonding, but the electrons are not transferred, they're just shared, and the electrons have an attraction to the nucleus of both atoms involved. Bonds are weaker than ionic, thus having lower melting and boiling points. And these are non-electrolytes. They don't dissociate in solution, and so therefore the solutions do not carry an electrical current when present. Metallic bonding. These are special types of bonding that's due to a delocalized system. And what that means is that the electrons are free to move across the surface of the metal. And a lot of times they call this, they give an analogy of a sea of electrons floating across the surface. They move freely, and this makes them excellent conductors of electricity. Okay, so now we are going to talk about nomenclature or naming compounds. And the first type of compounds that we will talk about are how to name ionic compounds. And within ionic compounds, you have fixed charged metals, and then you have non-fixed charged metals. So the first type we will be covering are the fixed charged metals by nonmetals. Now these are typically the main group metals, the tall groups on the periodic tables, group 1, group 2, group 13 through 16, the metals in those groups. There are some exceptions, and we'll point those out here in a minute. So we will do examples. When we're given the name, write the formula, and then given the formula, write the name. Our first example here is sodium chloride. So if we were to write the formula for this, we're given the name. You just write the symbol, and then you need to note the charges of them. You don't need to leave them up here, but it's always good to make note of the charges. And you'll notice here that with sodium chloride, we have a +1 and a -1. So we have a 1-to-1 ratio of atoms. And if there's no subscripts down here on the bottom, that is, the default is 1-to-1. Okay. So let's see how that plays out with ones that aren't a 1-to-1 ratio, like magnesium bromide, for example. So let's write that down. So we got a +2 charge and a -1. So remember, on the periodic table, the group 1 metals tend to lose 1 electron to become positively 1 charged. The group 2, which magnesium falls under, loses 2 electrons to become a positively 2 charged. And if it helps you, you can write those charges on your periodic table to keep note of those. So group 1 would be +1, group 2 would be +2. Group 13 would be +3. We skip over group 14, then 15, 16, 17, and 18. 18 doesn't tend to create ions, so it would be 0. 17 would be -1, 16 would be -2, and 15 would be -3 anions. And so magnesium is over here somewhere, so it's +2. Chlorine is in group 17, so it's -1. So notice here, to make this a charge-neutral compound, we need 2 bromines per every 1 magnesium. So you would cross down the charge here, and it would be MgBr2. The 1 is understood, so you don't need to write it down. Aluminum oxide, let's do that guy. Al and O. Aluminum is in group 13, so it's +3. Oxygen is in group 16, so it's -2. -2 and +3 here. So then you crisscross the charges. And for every 2 aluminums, you need 3 oxygen atoms to make it a charge-neutral compound. If you want to double check yourself, you can multiply the number of atoms by the charge. 2 times 3 is 6. 3 times -2 is a -6. So those would add up to equal to 0 there. Okay. So now, if we are given the formula, we write the name. So here we have calcium and oxygen together. So you write down the name of the metal and the name of the nonmetal with an IDE suffix. So this is calcium oxide. Okay, let's do another one. Potassium phosphide. Alrighty. And then magnesium bromide. Very good. Alright, so those are the main group metals by nonmetals. There are 3 exceptions to that, and let's go over those. They are tin, antimony, and lead. So let's write those down. Tin. Oops. So we're on the next slide. So let's just write those above here. Let's see if I can get my... So all 3 of those are in the main group, but with those, these are variable charged. So they will need to have Roman numerals in the name, like these other variable charged metals. So now we'll talk about variable charged metals. And these, you'll need Roman numerals to denote the charge. These are typically the transitional metals that carry multiple oxidation states or charges. And so in the name, you have to note the charge of the metal with a Roman numeral. And so let's go over how to do that. Let's first, given the formula, write the name. And then given the name, we'll write the formula. So this first one is vanadium and nitrogen together. So how would we name that? So it would be vanadium, some Roman numeral to denote its charge, and then nitride. Alright, so how do we determine the charge up here of the vanadium? Well, you have to look at the nonmetal side and calculate its charge, and then use that as your guide to cancel out that charge with the metal charge. So nitrogen is in the -3 group. So -3 times 2 gives us -6. So we're going to need a charge of +6 to make this whole thing equal to 0. So you're asking yourself, what 3 times what is equal to 6? Well, the answer there is 2. So it's vanadium, Roman numeral 2, nitride. All right. So nickel is also another transitional metal. It's in group 10. And so you'll know that all the ones in the middle, there's some exceptions, and we'll cover those here in a minute, need a Roman numeral to denote the charge. So let's do that one, nickel, some Roman numeral, bromide. So bromine is -1. So this whole side's -4. So this side's got to be +4 to make it equal to 0. Okay. So we only have one nickel because it has no subscript by it. So we know that the nickel is going to have to be 4 for the Roman numeral. So it's nickel 4 bromide. The 4 is a little funky looking there, but you'll forgive me. I hope. All right, so that's nickel Roman numeral 4 bromide. Titanium is another transitional metal, so it has multiple charges or oxidation states. And so we have to figure out what that is. So we have titanium, some Roman numeral sulfide. Okay. So sulfur is in the -2 column. So -2 times 1 gives us -2. This side has to be +2 to make the whole thing equal to 0. So 2 times what will give us 2? Well, 2 times 1 will. So this is titanium 1 sulfide. It's important to note here, even though it's a 1, it's not understood to be 1. So you have to use the Roman numeral here, make a 1 there, titanium 1 sulfide. All right, so we've covered how to write the formula given the name. Now let's go and write the formula from the name. And here we've got copper chloride, right? Copper 1 chloride. So Cu and Cl are the symbols for those two elements. And copper is in the transitional metal, so we don't know what charge it is just by its position on the periodic table. So we are given that in the Roman numeral here. So it's copper plus 1 chloride, and chlorine's -1. So it's a 1-to-1 ratio, so it's just CuCl without any subscripts down there. Remember, if there's no subscripts, it's understood to be a 1 for the Roman numeral. All right, iron 4 sulfide. Let's do that one. So iron is Fe and sulfur is S. Iron, we're given the charge from the Roman numeral is 4 and sulfur is -2. So it's 2 and 4 there. So now we notice that those are multiple of each other, so you can reduce it. So it would just be FeS2. 2 goes into 2 one time, 4 goes into, or 2 goes into 4 2 times, so it would be FeS2. So you kind of have to watch out for those that you can reduce down. All right, let's go and do manganese 3 selenide. So manganese is Mn and selenium is Se. Got +3 for manganese, and selenium is -2 in the -2 column. So we'll crisscross those, Fe2, Se3. Okay, so that's the general gist of it. We have some exceptions here. We have tin, antimony, and lead that you'll need to do this Roman numeral thing for. And those are in the main group. They're in groups 14 and 15. And then there's 3 transitional metals that have a fixed charge that you don't use Roman numerals for. So you don't use Roman numerals for it's silver, cadmium, and zinc. Silver is always +1. Cadmium is always +2, and zinc is always +2. So for those 3, you just name them like you normally would. Let's do an example. So let's say that you had silver sulfide, for example. So that would just be silver sulfide, right? Because it is always +1. You don't need a Roman numeral to name that one. All right, let's do an example of one that you would use, that are in the main group that you would use Roman numerals for. So let's say that you had Pb, let's say 3N2. So this would be lead. Nitrogen's -3, so this would be -6. So this has got to be 6. So 3 times 2 will give you 6. So this would be lead 2 nitride. Okay. So some good examples there, and we will have a chance to practice this more as time goes on, and we'll do a mixed set of nomenclature in a bit, and you'll see how that works. Okay. Ionic compounds involving polyatomic ions. Cool, cool. Fixed charge metals by polyatomics. Given formula, write the name. And given the name, write the formula. So we'll do some examples here. The first one we'll do is calcium phosphate. Okay, so when writing these, you write down the name of the metal and the name of the polyatomic ion. Notice here that the polyatomic ion does not have an IDE ending like a regular element. It has an ATE ending. And so it's extremely important that you learn polyatomic ion names, and hopefully your instructor has you well on the way of learning all these. Until you get the hang of it, you might just keep a list of polyatomic ions next to you. All right, so this is rubidium, and this one is perchlorate. Okay. So this one's in a series. This polyatomic ion is in a series of polyatomic ions. You got hypochlorite, which is ClO. You got chlorite, which is ClO2. You got chlorate, which is ClO4 or ClO3, and then you got perchlorate, that's ClO4. So hypochlorite, chlorite, chlorate, and perchlorate. We're going from ClO all the way down to ClO4. And then this one is strontium, and this one is the first one in the series, and this one's hypochlorite. That's an R, by the way. C-L-O-R-I-T-E, hypochlorite. Now you'll notice with these you don't need a Roman numeral because the charges of the metal are fixed. They're in the main group. You have to watch out for the exceptions, of course. But they're all fixed charge, so you don't need to write a Roman numeral next to them. Okay, so now, given the name, we are going to write the formula. So ammonium is NH4+, one of the few polyatomic ions that have a positive charge. And then phosphate is PO4, -3. Okay, so now when you have polyatomic ions and you have more than one, to denote those, you need to crisscross the charges, but you have to put parentheses around them so you don't mess up the number of atoms. So here with ammonia, we're going to put a parentheses around it and a 3. And since it's +1, the 1's understood, so you don't have to put parentheses around there and put the 1 on the outside. So for every 3 ammoniums that are +1, you can have only 1 phosphate, which is -3. So the charges equal out, +3 -3. Aluminum sulfate, let's write this one over here, AlSO4, so -2 and +3. And so now we've got to crisscross the charges to get the charge neutral compound. So you got a 3 there and a 2 there. So you have a grand total of 6 on both sides, 6 and -6. 3 times 2 makes 6. 3 times 2 makes 6 here, and 2 times 3 makes 6 there. And then magnesium nitrite. Okay, so magnesium is Mg, nitrite is NO2, -1. Magnesium's a +2, so you crisscross those and you come up with MgNO2 too. All right, very good. So let's see what is on the next slide. I believe variable charged metals by polyatomic ions. Given the formula, write the name, and then we'll give the name and write the formula. Okay, so we have vanadium, which is a transitional metal. So that's a key there. Need Roman numerals, right? And we have PO3, 2. Okay, phosphite. Okay. So one way of recognizing the polyatomic ions is you have poly means many. So you have more than one element in that second part of the name. So that's a dead giveaway that you got a polyatomic ion. So here, let's write this one, vanadium. We'll leave a space here for polyatomic ion, and then we have phosphite. Okay. So now we need to figure out what the charge is of that metal in the compound. So we look at the nonmetal side and then equal them out. So phosphite is -3. -3 times 2 gives us a -6. So this side's got to be 6 to make that equal to 0. So 3 times what will equal 6? Well, that's 2. So there's our squiggly. Sorry about that. So Roman numeral 2, vanadium 2 phosphite. Okay. All right, so now we have copper and perchlorate. So copper is Cu, some Roman numeral, perchlorate. Okay. So perchlorate is -1. So this side's got to be +1. Now, sometimes I've seen students want to multiply the -1 times the 4. But remember, that polyatomic ion is like one big unit. So it's ClO4 and it carries a -1 charge. And so that incorporates, that -1 incorporates the 4 oxygen atoms. It's not -1 times 4. So it's copper 1 perchlorate. And if you get confused about those types of things, you can always draw parentheses around the polyatomic ions to denote that that's like a single element. Okay, let's do another one. Why? Because they're so much fun. All right. All right, so now we got manganese, M-A-N-G-A-N-E-S-E, manganese, some Roman numeral, and this is hypochlorite. The ones with fewer number of oxygen atoms in a series have an ITE ending. Okay, so just like all the other chlorinated polyatomics, this one has a -1 charge. So this is -4. So this side's got to be +4, right? -1 times 4 gives us -4. So it'd be manganese, Roman numeral 4, hypochlorite. Remember, the charge up here gives you the Roman numeral of the polyatomic ion. All right, so now we're going to go back the other way and write the symbols given the name. And I think this is actually a little bit easier. So chromium is Cr, and phosphite is PO3. And with this one, chromate is +2 because it's given to us in the name, and phosphite's -3. So we got 3 and 2 here. All right. So now that is charge neutral, +6 on one side and -6 on the other. Thallium, 4 sulfite. Okay. So this one, TL and SO3, SO3, -2. Okay. And this one's +4 because we're giving it in the name. Okay. And so this one is another one of those exceptions. It's in the main group, but it needs Roman numerals in the name. And so we will crisscross these. I was looking to be sure. I thought that I was right. And now you'll notice that these can be reduced. So it would just be TLSO4 and 2 there. 2 goes into 2 one times. 2 goes into 4 2 times, so you just reduce it down. Scandium 3 hypochlorite. So scandium is Sc, hypochlorite is ClO, right? It's the first one in the series. Scandium is +3, hypochlorite is -1, and so you have to crisscross the charges here. ScClO3. So there you go. So we'll do more practice with those in mixed sets and individually in your worksheets. Covalent nomenclature. Okay. There's bad news and good news. The good news is, well, let's just start with the bad news. The bad news is there's 2 rules. The good news is there's only 2 rules. And so it makes it pretty easy to name these. And you already know the names of some of them. So you use a prefix to note the number of atoms on the first name unless a single compound or single number of atoms. And then you use a prefix to note the number of atoms on the second name plus an IDE ending. So we'll use these two rules, and you probably won't even need the rules after you've done some practice. So here are the prefixes for the number of atoms. Okay, so we're going to put up the two rules, and then we're going to go through and do examples. So this first one is, if you're given the names, you write down the symbols. So carbon dioxide, and you probably already know that that is CO2. Okay, so here you'll notice that it doesn't say monocarbon dioxide. If it is a single atom, you don't on the first name, you don't put a mono on it. You only put a mono on it on the second name if it's a single atom. And so we got carbon tetrafluoride here, carbon tetrachloride, I think I might have said fluoride. And then this next one, we've got dinitrogen pentaoxide. So N2O5. Okay, that's always a nice reference to have while you're naming these. All right, so now we're given the names and we have to write the formulas. So you always use a prefix on the first name. You use a prefix on the first name with the exception of single atoms. So this one, you got 2 nitrogen atoms. So you got 2 nitrogen atoms here, so it's going to be dinitrogen and monoxide to denote 1, right? So the only time you'll see mon is in the second name. So this is carbon monoxide. Carbon monoxide is the byproduct of burning fossil fuels in an environment where you have limited oxygen. And so this is a very deadly gas. It can cause you to have severe health problems if it's breathed in. And now we have sulfur, hexa, S-U-L-F-U-R. Sorry about that. Hexafluoride. Sulfur hexafluoride. Very good. So those are easy to name. The main thing is to recognize when you have the symbols is that you have 2 nonmetals together. There are some exceptions to that where you have a metal and a nonmetal really close together on the periodic table, and they have very similar electronegativity, so they actually share electrons. Those are few and far between, so we really won't go into those since we're talking about general naming schemes. Acids and bases. Okay, so we'll kind of conclude our discussion here of nomenclature and whatnot with a discussion of acids and bases. And acids are substances that donate hydrogen ions in water. And this is what we call an Arrhenius definition of an acid. Acids, since they donate hydrogen ions, if you look at a hydrogen ion, well, hydrogen only has 1 electron. And so if it loses that electron, the only thing left is a proton. And so we say that acids are protonated or have a lot of protons, in solution. And that's the Bronsted-Lowry definition, protons. They have protons in solution. And this also allows you to have a definition that's not water-based as well. So Arrhenius that definition is only good in water, but you can have gaseous acids as well, and so those you would think of as being protons in that gaseous state. Bases are substances that donate hydroxide ions in water. So hydroxide ions, and just like the Bronsted-Lowry definition on acids, bases accept those protons, and so the Bronsted-Lowry definition can be outside of water. So you don't have to have, it doesn't have to be an aqueous solution to be a base as well. Properties of acids and bases. So here, acids have a sour taste. You should never taste anything in the chemical lab, of course, but one of the things that you can think about is things like citric acid, like in grapefruits and so forth. It has kind of a sour taste to it. And then have a pH lower than 7. We'll talk a little bit more about the pH scale in the following slides. Our electrolytes, when they are in aqueous solution, they conduct electricity, react with metals to form gases. We've talked a little bit about the bases the alkali metals reacting with water to form hydroxides, and that would be a base, and hydrogen gas. Well, acids react with metals as well to form gases. Terms blue, litmus, red. There is a dye that turns red when in the presence of an acid and reacts with bases to form salt and water. And let's just do a little example of that while we're at it. So let's take hydrochloric acid, and let's take sodium hydroxide, which is a base. And what happens is these bonds split and these bonds split. So hydrogen will react with hydroxide, which is water, H2O, and sodium chloride, which is the salt. So this is a specific example of an acid-base reaction that forms water and salt. Bases are bitter to the taste. If you're ever singing in the shower, most soaps are slightly basic. And you get a little bit of that in your mouth, and it's very bitter, right? Have a pH greater than 7. Our electrolytes also, so that's something that acids and bases have in common. They kind of feel slimy to the touch. They turn red, litmus, blue, and they react with acids to form salt and water. Here's our base, sodium hydroxide forming in water. Hydrogen chloride, or a hydrochloric acid, we'll talk about names of acids here in a minute, that produces the hydrogen ion. And so that's very typical of any type of acid-base reaction. The pH scale, okay, let's talk a little bit about pH. pH is a logarithmic scale, and the pH is equal to the negative log of the hydrogen ion concentration. And here we say that the pH, if it's less than 7, it's acidic. If it's 7, it's neutral. If it's greater than 7, basic. You probably went over this in biology class at some point. And this is a kind of cool little Wikipedia graph that I pulled up. So battery acid is less than 1 on the pH scale. So it's very, very, very acidic. But remember, the lower the number, the more acidic it is. And the higher the number, the more basic it is. Gastric acid that's in your stomach that helps you to digest your food is between 1 and 1.5. Vinegar is 2.5. Okay, so it's a relatively weak acid. Orange juice has citric acid in it, 3.3 to 4.2. Black coffee is is a little less acidic than orange juice. And then milk is very close to neutral, 6.5 to 6.8. And then pure water is 7, and then seawater is 7.5 to 8.5. So you can have seawater can be slightly basic to even more basic depending on the where you pull your sample. One of the controversies in science now is about acidification of ocean water and how that affects coral formations and so forth. And so that's one of the hot environmental topics of the day concerning pH. Salt water has a better buffer than fresh water, if you have large industrial plants that the exhaust is not scrubbed properly, you can get what we call acid rain. And acid rain can go into the streams and cause fish kill because their pure water doesn't have quite the buffering system and can't accommodate that change in pH. Okay, so we got strong acids and weak acids. Strong acids totally dissociate into ions, and they have a lot of ions in solution, so that hydrogen ion concentration bumps way up, and you have a very low pH. Since it's the negative log of that, you have a low pH with that. Weak acids, like acetic acid or vinegar, only partially dissociate. So in solution, you have a lot of the acid itself that's dissociated. You have very little of these ions in solution. And you have what we call an equilibrium here, which we will cover a little bit in our last unit. Strong versus weak bases, the same situation applies. Strong bases totally dissociate. Sodium hydroxide is a very strong base. So you have almost all of the solution in the ionic form. You have sodium ions and hydroxide ions. Of course, hydroxide ions are the ones that cause the solution to be basic. Ammonia is a weak base in solution, and you have very little hydroxide ions in ammonia, or very low concentration, I should say. So now we are going to talk about nomenclature of acids, or naming acids. And there's basically two different types of schemes. The first one we'll talk about are binary acids. Binary acids only have two elements in the name. And so with these guys, you use the prefix hydro and the suffix ic. And you can recognize these because they will have a AQ by them, like so, which means that they're in aqueous solution. And they will have a leading hydrogen ion. So this one is hydrochloric acid. Notice here the hydro and the ic. Okay, so you drop the last part of the chlorine and you add ic to it, and you put hydro in front, and then the word acid, hydrochloric acid. And this one here is hydroiodic acid, hydroiodic acid. And so if you only have two elements, a hydrogen and another element, this is how you name those. Of naming scheme is with acids involving polyatomic ions. And so with these, you use a different type of naming scheme. We say that eights are icky and ites are us. So if the polyatomic ion ends in ATE, you use the ic, and if it ends in ITE, you use the us suffix. You don't put any prefixes on them, just suffixes and acid. Okay, so here our examples are sulfate. This one involves sulfate, H2SO4. So sulfate, it's an 8 acid, so it would be an icky acid, so sulfuric acid. Sulfuric acid. Sulfite, right? So ites are us. Okay, so this would be sulfurous acid. So pretty cool, right? Not too bad, but you have to know the names of your polyatomic ions. That's the downside of it. So let's do another example of this one. These are a little bit harder. HClO4AQ. Okay. So I know this one is perchlorate. So it would be perchloric, sorry. Perchloric acid. Remember, 8s are icky. 8s are icky acids. So that's that. Okay, so now let's take a look at a strategy for naming a mixed nomenclature set. And so what I always do is I keep in mind this flow chart, and I think it's helpful for students when they first start looking at mixed sets to kind of have something to help guide them, and then after they have lots of practice they won't need to refer to the chart. But I've written a chart over here on the left hand side, and it all depends on that first element. So you key in on that first element. And so pause the video here and write down the flow chart, and then we will use the flow chart to go back and do these this mixed nomenclature set as an example. Okay, hopefully you've done that. And so what you do is you key in on the first element and you ask yourself, is it a metal or is it a non-metal? All right, so in the first example here we have manganese, and it's a metal. So then we ask ourselves, is it a transitional metal or is it a main group metal? Remember, the transitional metals are the ones that are in the middle of the chart. They're transitioning to non-metals. And the main group metals are the ones in the tall groups. So we find manganese, and manganese is in group 7. And so it is very definitely a transitional metal. So here it says use Roman numerals in the name. So we got manganese, some Roman numeral, and then sulfate. Sulfate is a -2 charge. Well, -2 times 2 gives us -4. So manganese is going to have to be +4 to cancel that out. We only have one manganese atom there in the name, or in the symbols. So it's going to be manganese, Roman numeral 4, sulfate. All right, so let's continue on. And the next one we have silicon. So we find silicon in group 14, and it's on top of that stair-step line. So silicon is a non-metal. So we look at our chart here, it's a non-metal. So we know it's a covalent compound, and we use prefixes for covalent compounds. So this one is silicon trioxide. So notice here we didn't say monosilicon, because remember, on the first, you only use prefixes on the first name if it's more than one. So this one is silicon, and you always use prefixes on the second name, silicon trioxide. All right, let's do the next one. Calcium. Calcium. So calcium is in group 2. All right, so it's a main group metal. Okay, so we don't use Roman numerals. It's not one of the exceptions. So this one's calcium, and it's a single element. It's not a polyatomic ion, so it's the name of the nonmetal in an IDE ending. Nitride. Okay. All right. So now we have tin. SN. So we find tin, and tin is in the main group, right? But it is an exception in the main group. It's in the main group here, but it's an exception, so we don't use Roman numerals for that. So this one would just be 10. Oh, I'm sorry. Oh, we do use Roman numerals for it. Usually in the main group, you would not use Roman numerals, but since it's an exception, you use Roman numerals in the name. So it'd be 10, some Roman numeral, sulfate. We recognize the polyatomic ion. It has more than one element in the second part of the name. It is the sulfur polyatomic ion with more oxygen atoms, so it's ATE. It's a -2 charge, and there's just one of these, so this whole side's -2, so this has got to be +2. 2 times 1 gives us 2, so it's 10,1 sulfate. All right, so now we have some names that we've got to write symbols for. These are a little bit easier because you are given the Roman numerals when you need to use them. And so on this one, you got vanadium, 3 permanganate. The hard part here is remembering the charges of the polyatomic ions, and you should be working on those to get those memorized. So then you crisscross the charges. So -1 times 3 gives me 3. 1 times 3 gives me 3. So 3 plus a -3 gives me 0. So calcium nitrate Nitrate's -1, calcium's +2. So you write the symbols and you crisscross them. Aluminum sulfide. Okay, tricky, right? IDE, so you know it's a single element. So aluminum is +3, sulfur is -2. And there you go. There are a lot of practice problems in the problem set. Please do them all. And if you don't have enough practice, then cover up the problem and take the solution and work backwards to the problem. So you have actually double the practice problems if you use them that way. So I hope you've enjoyed this recording on nomenclature and the review of the different types of bonding. Looking forward to seeing you guys in Unit 6, which is chemical reactions. And we'll use a lot of the same skills in putting elements and compounds together in that unit as well. Have a great day, and we'll see you in Unit 6.